you. My name is Aslı Akçamete Güngör. I'm an assistant professor in Middle East Technical University. I will present you our work with my co-author here, Dr. Çağla Meral, and my PhD student, Usman Hasan, on investigation of the terrestrial laser scanning reflectance intensity with the goal of assisting construction material identification. I think, as you know, the laser scanners are the active sensors that emit the coherent and single frequency near infrared laser pulses, and the terrestrial laser scanners are the ground-based laser scanners that we are also currently using in our studies, which are usually mounted on a tripod. In construction sector, laser scanners are the very commonly used 3D data collection methodology right now, and we see that it is used for many different purposes, for structural health monitoring, for example, for damage assessment, deformation measurements, deflection measurements or deterioration of the materials, as well as for topographical studies, for earth volume calculations, material quantification, for progress monitoring, for construction management. And also 3D models are now being built, as we have seen some example studies here also, for the as-built capturing and as-is modeling. But for all of these, or most of those use cases, we actually need some more information like material information. And we have a lot of different types of materials, as we know, we use in the construction or in structures, especially in buildings that we focus on in our study. We use commonly concrete as a structural material in reinforced concrete structures common in our area, and also block units like clay bricks and lightweight concrete blocks for partitioning, for exterior enclosure, sometimes for structural purposes and insulation purposes. These are only some examples, but you can guess that there are a lot of different types of materials. And actually, it is not a very easy task to identify all of these materials accurately, timely, and continuously during the construction, and also for as-is building model generation. So material information becomes very important for us in construction management and in some other purposes like interim payment certifications, for scope verification, for quantity takeoff calculation. If you know what type of material it is, you can have the associated cost with it to calculate the cost information, or we can even need it for energy performance analysis. We need to know the type of the equipment, the material that we are using. So this information, the material information, can only be used if we can identify the material correctly. And currently how we do it is usually, mostly, by humans. So when the humans are involved, it is usually error-prone, sometimes unreliable, and it takes a lot of time when you need to do it continuously during the construction. But for the future, we try to achieve an automated version of the material identification, which will eliminate the humans in the process, and it will more timely and more accurate when we can enable this in the future. But for also getting to the analysis and using this information requires not only data capture that we can currently do with the laser scanning, but we need some semantic information in these models. Currently, this is not used or underutilized from the laser scan data. So we usually get the geometric information, and geometric information is obtained from the point cloud data. And this is converted to the 3D model, usually with a semi-automated manner. So those semantic information is manually added. We select the type of the components or the material types. However, if we can use this functional information, which is a basic requirement for the semantically rich information models, we can do more. We can do some other analysis that I have given some examples, like structural analysis or some performance analysis that we can do. So laser scanning data not only contains the geometric information, but it also has some reflectance intensity values in it that can be potentially used for adding this functional information into the building information models. So our goal is to develop a robust method for material identification through laser scanning and assisted with images with RGB values, which can provide foundation for progress monitoring, scope verification, and quality control. But this paper focuses only in the initial stages of our studies in achieving this goal. So we looked into the effects of reflective surface properties and on the reflectance intensity and RGB distributions within the scope of this paper. So I would like to explain you our methodology in 4 parts. I will explain the equipment that we have used, the materials that we have tested, the measurement conditions, and the post-processing steps that we have followed. So the boxes in the darker blue are the ones that we have currently performed, or the parts that I will explain to you. And the light blue ones are our future work that has not been completed as yet. So we use, of course, the laser scanner, but the image information only comes from the inbuilt camera of the laser scanner. We have not used any external cameras for now. Materials only tested at the lab conditions. We have not scanned anything at the actual site conditions currently. Measurement conditions, the things that we think it affects the intensity distributions. So we used different illumination conditions and surface moisture conditions, but we have not changed the distance and angle of the measurements for our current tests in this paper. For post-processing, we identified some material signatures for the samples that we tested, but we have not currently compared the comparison with a similar type of material from the job site or from other samples to see if the signatures match with each other or not. As you may again know, there are 2 common principles of taking measurements with TLS, phase space and time of flight. And each of them have their own benefits and limitations. One of them is more faster, one of them has a better range, that kind of a difference. The scanner that we used is a newer technology that uses time of flight with waveform digitizing technology. It's a Leica P40 laser scanner. Since it is using a newer technology, it actually takes the benefits of both methods, time of flight and phase of the other type. So the range is up to 270 meters, and it can actually scan 1 million points per second. So it is a lot faster also from the older type of time of flight scanners. So this is the scanner that we use, the equipment, and the samples that we used are those 3 samples, like the concrete, the lightweight concrete, and brick samples at the job at a lab environment, as I mentioned. So the colors of the concrete, of course, light gray to gray, but the brick has a very different brownish orange color, a different sample among the others. Their surfaces have different characteristics, smooth to porous to textured. Those materials are different. And the areas here you see are the large and small areas, post-processing areas that we use from the samples that we have tested. So I will explain the results later, but we used a larger sample area versus a smaller sample area from the same surface to see the differences in the signatures of the reflectance intensity. Those are the experiment conditions that I mentioned to you. We tried in high and low ambient illumination. So the location that we did tests were a lab room without any windows, so there were only artificial lighting, no daylight affecting our experiments. So we turned off the lights and we did the same scans in a dark environment. We put all of our samples at 3 meters away from the scanner at almost the same level with the scanner to eliminate the change in the distance and the angle as much as possible. And we also tried the as-is versus the moistured surface of the samples. So we collected the data from Leica, and then we used Cyclone software to parse this data, raw data for post-processing. So we selected an area, as I said, we try to limit the angle of the scanning to not to get too much of the environment, but still we get some part of it. So while illuminating, we didn't get the edges of the components because there are more noise about and different parts of materials can come to that. So the larger area is the largest that we can get without the edges, and we also get some small areas that I will explain. And our output is given here, X, Y, Z, I, R, G, B, for the each acquired point. So this is, the output includes X, Y, Z Cartesian coordinates. The I is the scale reflectance intensity, we call it II, and I will call it I from now on, which is linearly scaled between 0 to 1 within the scanner. So, and then we use RGB, which is an 8-bit integer from 0 to 255. So we use this ratio of the reflected to incident radiation from the scanner for the intensity value, and difference in the intensity, in the I values related to material composition, as well as some environmental conditions, such as illumination angle of reflectance and color of materials. So our goal is to find out the effect of the material on this change. So we are trying to figure out if different materials have different reflectance intensity signatures. So these are some examples in the literature. They looked into identifying those materials with I. So for clay contents of rock samples, moisture contents, types of wood, etc., can be actually identified by using reflectance intensity. We also use red, blue, and green values. As I mentioned, we use the inbuilt camera, which is not a very powerful camera, but we use the values from that charge couple device included inside the laser scanner. We did some post-processing. So Cyclone output is exported for further data analysis. There we linearly scaled the RGB values also from 0 to 1. And for each scan, we created an IRGB distribution of the selecting scan areas by representing in histograms. So this is our results for intensity distribution. For the large post-processing area, you see different colors. The concrete is in darker color, a light white with a grayish outline, and brick is in orange. So you can see these different components, different materials have significantly different intensity histograms. So we can actually identify different materials by looking at these different histograms. However, this is not enough because we also need to have these results repeatable. So we only have one set of data on one set of samples. So we first wanted to look into other areas from the same sample. So we randomly selected small areas from the scan data, and when we compared the histograms, we see that there is not any significant difference between the whole area of the surface versus the small area of the surface. So you can see here in these figures for the concrete, lightweight concrete on the left bottom and brick, both of the large area and small areas are put on top of each other. It's almost same histograms that we got for intensity distribution. So for high and low illumination, on the left is the original, and on the right is under low light conditions, basically. So we have seen that different illumination levels show no significant difference. So it's also a benefit of laser scanning that it doesn't require light like cameras to capture data. So since it has its own source for emitting the laser beams, we were able to capture the same signature without light in the room. Lastly, we checked the moisture conditions, and we have seen that actually humidity is affecting the intensity distributions a lot. So you can see the difference on the right. The wet samples, the intensity histograms shifted towards left. So because of the thin film of the water on top of the surface, some of the laser beams are emitted, some of them are reflected, and it changed the characteristics, the signature of the specimens that when we collected the laser beams. RGB distributions show that it's not very significant as the intensity distributions when we only use the image data, RGB, RG, and B graphs separately. we can see that when we compare the concrete and lightweight concrete, both have some shades of gray, so they broadly overlap, although they are not exactly the same. But the orange color of the brick is considerably different than the other components. And actually, this information is also affected with the sensor type, temperature, lighting conditions, so we cannot use this as a single source for identification of the material. In summary, usually the 3D model automatically generated from laser scan data lacks the functional information, which is actually very beneficial for a semantically rich model and for doing some different types of analysis. And in our study, we tested some samples in lab conditions and have seen that actually the reflectance-intensive distributions can be used successfully to identify, differentiate different types of materials. As a future work, we would like to do some more tests with different types of samples at also job site conditions to see if we can repeat these same results. And also, we would like to add RGB values as a secondary parameter for material, helping the material identification when we cannot differentiate with the histograms. So, as a conclusion, we think that TLS has a potential for augmenting the visual material identification processes that are currently being done manually. This is the end of my presentation, so thank you.